We will solve this today's LeetCode problem. This is a minimum height tree and this is a medium problem. Let's see what it is. So it is given a tree is an undirected graph which is has any two vertices are connected by exactly one path. Okay. And we have given a tree of node level from 0 to n minus 1 and an array of n minus 1 edges where edges I is connected to these two vertices indicates that there is an undirected edge between the two nodes ai and bi. So it is simply a you can say it as an undirected graph, right? So you need what we need to do here. So we need to choose any node of the tree as a root, and when you select node x as the root, the result tree has a height h. Among all possible rooted tree, those with minimum height are called minimum height trees. So return a list of minimum height trees root labels. You can return answer in any order. So what we need to find here, so suppose a tree is given 0 1 2 3 first thing. So we need to make every node as a root and then find its height, right? And and like that we will choose every node as a root and find the height, and among all of them we need to see which is the minimum height in all of the combinations, and if there are many minimum heights possible for different routes, we need to return all of them, right? Okay. So and that's the question behind that, right? So if you see the first example, this is given 0 1 2 3 like that, right? So first we make a 0 as a root, so what will the height? 2 will be the height here, right? When we make 1 as a tree root, then 1 will the height. If we make 2 as a root, then 2 is a height, and when we make 3 as a root, then 2 will be height. So the minimum of all possible height is 1. So and what root it will be taken? Only one, so only one is written, right? If you see in second example, if we made every node as a root, then we will see that the minimum height will be only 2. If you take 3, then minimum height will be 2. If you take 4, then minimum height will be 2. Otherwise if you take 5, it will be 3 height, right? And otherwise you 0 1 and 2, it will be 3 height, so minimum height will be 2. So you need to take only those root node as a root which has minimum height. So 3 and 4 both will be the answer here, right? So what should we what how should we think here, right? So the first approach, which the first intuition that should also come in your mind, that we will we will uh, we will make every node as a root, right? Every node as a root and find the height of the tree, right? And then store all the heights with their nodes, and the height which is minimum and the height which is minimum among all of them, we will return their nodes as an answer, right? Right, this first thing you should this should come in your mind always, right? But what there will be the problem here, that if I choose every node and find its height, and so finding a height with one node takes o of n, because I need to traverse in all of the tree to find height. So for every node it's take o of n, and there are n nodes, so that will be O of n square, which is not optimal, right? Which is 2 into just because constants are 2 into raised to power 4, so this will be 2 into of n square. This is not optimal, so this is not optimal. So let's think this another way, right? So if you observe here that what will be the what will be how many nodes can be there so that the minimum height always occur. How will be the how many nodes are there for the minimum heights, right? So if you observe, the minimum heights will be the minimum height will be what? If I choose, say if I choose a leaf node, if I choose a leaf node, Just think like that. If I choose a leaf node, should okay, will we get a minimum height? Will we get a minimum height? Think on this. No, no, we don't get a minimum height. We will get a maximum height if we choose a leaf node. So leaf node cannot be an answer, right? So leaf node, if there is leaf node cannot be an answer. So what should be can be the answer here? So leaf node is not an answer. So the nodes which are in mid of the tree can be an answer, right? So the nodes which are in mid part can be an answer, can be an answer, right? So the nodes which are in mid of the tree can be an answer, right? So how will I find the mid nodes, right? How will I find the mid node of a tree? So for finding the mid node, and okay, so one observation is also here, that how many nodes can be an answer, at most how many of nodes can be an answer. So if you observe, there will be at most two nodes can be an answer. How will I come up to this? Let's think, right? So this is given 0 1 and 2 3. So suppose here it is given, so I need to see the mid part, right? So if I start from leaf node and start deleting it, if I start from leaf node and start deleting it which has not connected, so suppose I have deleted 5 0 1 2. In the example 2 I have deleted 5 0 1 2. So what will you left? It will be left 3 and 4 only, right? So let's suppose, how will I make it stand this? So let's suppose this is given, this 4 5 again, and this 4 5 3 3, and this is 0, right? So how will I 0 1 2 0 1, and this is 2, this is 2. So how will I suppose, and there, so suppose there are other nodes as well. Suppose here is another node 5. This will be, oh, this will be 5 again in this part, which is, suppose this is a 6 given, right? So if, so if in this case, let's suppose the leaf nodes are 6012, that cannot be an answer, so we'll remove this. So 5 3 is also cannot be an answer. Why? Because it is already connected with this 4, right? So because 5 3 is already connected with this, so if we choose 5, then the answer will be 3, because it is all, it can move to this 5 4 3 and 0, right? This can move to this 5 4 3 and 0. So if we connect with this 5 or 3, it will be 3 answer. So leaf node is not answer, 5 3 is not an answer, so answer will be only this 4, because it will be only the height of the true 2. So for along with, by taking some examples here, if you take like this example, or make another 3 as a root or 6 as a root. So if you write on pen and paper and make a graph of this, you will find out that uh, the we will cut out the start from the leaf node, and the leaf nodes which are left, and again if there are leaf nodes again left, we will cut out this. So this is something like topological sort, right? This is something like topological sorting. What will we do there? What we do in a topological sort? We make a we make a in degrees for every node. We make in degrees for every node, What is n degree? In degree is that how many is edges are coming towards this towards a particular node. How many edges coming towards a particular node? So let's suppose this is 5 here. So how many? What will the n degree for 5? This will be 2, because this 4 and 6 is coming towards 5. This 5 is 5 n degrees is 2, right? So what will the n degree for 6? This will be 1, right? So this is how we will find the n degree. And what we'll do in topological sort, we will start from the lower n degrees value and remove that as well, and again we will simply remove again and again and find the left part which has my last value, which is again right like 1 or again or 2. So only at most 2 nodes will be my answer, because due to this n degree part, if suppose this is 4 or 5 given, so this will be only 1 degree for 4 and 5 both. If you take any other 6, this will then n degree will be 5 for 2, so this will be the 2 height. So for minimum height, you need to find the last n degree value which is at the top of the tree. If you take an example of this, you will also observe that this is the topological sorting. Just we will need to find an n degree, and we start moving from leaf node and to the topmost root element, and we will get a minimum height. We will get all the nodes which has a minimum height possible, right? Which can be at most 2 value, right? So let's see how we will do that. This is all the part of observation and intuition. Now the approach is simple. Approach is simpler. That first we will find. First we will make our adjacency list for the graph, right? Because we have given edges adjacency list, and also store n degree for all the nodes. For all the nodes, then what we will do, we will simply start from the lower n degrees value of nodes and start removing them from tree, right? And also I need to reduce the n degrees of the parent, because of the adjacency of the adjacent parents, because because it is connected to that node which will be removed now, right? So their n degrees also will reduce, and now again we will see we will uh, we will uh, we will simply insert all the nodes which has lower n degrees after that, right? So the lower n degree, so what will the lowest possible n degrees? The lowest possible n degree will be 1, right? Because this is undirected graph, so lower possible n degree is 1. If it is a directed graph, then the lower n degree will be 0 possible, because both are not connected, right? This is for directed graph, and we have given undirected graph, so the 1 is possible. So the lower degree will be undirected, and lower degree n degree will be 1. So we will push all the nodes which has n degree is equals to 1, right? This is, and at last the at most 2 nodes will be my answer, right? So let's see how will we implement this. So what we need to first do, we will need to maintain a adjacency list and also in degree list. So for maintaining adjacency list, so this should be on your tip, or this should be mug up, because this will be used in many lot of graph problems. In this adjacency part, you need to maintain a n degree here. Okay, sorry, this should be n degree here, this should be n degree here, and this should be initialized with 0. Now I need to move in this edge, right? So what will we push? We will push this 0 dot pushback and even, right? So this is an undirected graph, so we need to push it vice versa also. So let's change it to this one, and this is 0 because both sides are connected. And also I need to push this n degree part for both of them, right? Because both are coming edges. Now you can use a recursion also, and we can also use a BFS part here. We can also use DFS and BFS for topological sorting, right? For topological sorting, but here I will use BFS for topological sorting because it reduce the time complexity. It will not take extra recursion stack space, extra recursion stack space, right? So let's see how we will use uh, queue data structure here for BFS. So BFS for BFS you mainly use queue data structure, right? So we will use a queue. What will we insert? We will insert the queue node part, right? So I need to iterate in all nodes. So what will be the starting point? So starting point will be the in degrees which is a lower. So lower will be the one. So I need to push all the nodes which has current in degrees as one value. So I will push all the nodes which has current is one. So I will push all the nodes. Now I will iterate in this queue. Okay. So we have come to a deduction that there will be at most two nodes in my answer, right? There will be at least two nodes in my answer. So and total number of nodes is n here, right? So can we write it like this, that if if my n if my n is less than 2, I will break this loop. So no, if n is less than 2, it means I have got the answer, right? Because at most the answer can be only 2. So if n is less than 2, we will return simply the answer. And what will the side will do? This will We will start from q, and we will insert all the adjacency part which has this node connected with, right? So we will start from all the adjacency part which is connected with. So if we will see also that this n degree of this node should be removed, x should be removed, because this node is automatically removed because we are starting removing from the lowest integers from the tree. So this node is removed. Suppose this is 2 here, this 2 is removed, so we need to decrease the integrity of 3 also. So that's why I need to decrease it, and I will check that if this integrity of x is 1, if it is becomes 1, then I will insert in my queue, because it is now become as a lower part, right? This is become as a lower as 1, right? So whenever I start treating an adjacency of some part, so I need to make its its parent or its child decrease value, decrement the value, right? So I will simply insert in my queue, and also I need to decrease my size here, decrease the number of nodes here. Why? Because if n is less than 2, it will break, right? and then simply I will return my. Okay, I need to also maintain a answer because I need to overall finally return a number of the exact node which has minimum heights. So for that, this queue should left some nodes with nodes because we have and less than 2, and this queue is should be left with some nodes. So this will be q dot front value, and we will pop this up till my queue is not empty. So I will just return my answer here, or I can also write like this: n is less than 2. Instead of this, I can also write like this, right? So I will return answer. So let's see where what happens. Okay, some wrong answers are here. So it is 023. uh, I think I some mixed some cases. This node, so I need to minus this index s, and we will push it up if my degree x is 1. Otherwise I will not push it up, right? How comes this 023 value? N is 3 in at starting, 0 1, n is 4 in starting. Okay, let's see what is C out, and let's run this again. So this q dot size is 3, and okay, we are not inserting in this loop. Why? Q dot empty should be 0, so it becomes 1, and n is less than equals to 2, which is correct. Mm, n is number of nodes, which is 4 given. Oh, okay, sure. Okay, this should be greater than 2. If it is less than equals to, it will automatically obey. Okay, sure. Now we can run this. Yeah, this should work here. Let's submit it. Let's run it again. Let's submit it. Uh, Something is missing. If one, okay, we missed the some edge cases. That if, okay, so if, what will happen if there is only one node? If there is only one node, which is edges, okay, okay, okay. So okay, we have missed the test cases that if there are no edges possible. I think we haven't get a constant here, right? Edges dot length let me 1 - 1, and can be a 1 only. Okay, so yeah, there can be possible that it has only one node. So if n is equals to 1 only, so in that case I will return simply 0 because so if there are only one node, so the answer will be the 0 because there will be no edges and no height of tree, so that will be the minimum possible values. So the answer will be the 0. But in our case, the answer is the answer is empty value. So yeah, let's run this again. Submit it. Hope that passed. Yeah, it went past. So we missed the edge case that if there are no edges and only one node is given, then the answer will be the zero. Only the root node will be the only the zero, because there is no answer. So yeah, I think we have successfully implemented the topological sorting. So this part is a this question is just like a topological sorting, just an observation after taking some examples here, right? We can also use a DFS approach. So okay, so what will the time complexity here in this case? So time complexity will be, we are we are iterating in all over the queue part, so that will over of all O of n, and also I need to move in all ages, which will take O of number of ages given, right? So this is O of e, and the number of nodes which is given is, suppose that is will be O of n, so that will again O of n. So this will be O of e plus n. So where e is number of ages and n is number of nodes here, right? And what will the space complexity? So the space complexity will be, we are taking extra adjacency list that will take O of n, and also I need to take a extra queue that will again take O of n, so that will be a overall of O of n. So this is the time complexity, and the space complexity will be, if you use DFS approach, that is recursion approach, then we will need to find we will need to take extra recursion extra time, which is O of n will be. So we are not taking that in this. So that will be we will using BFS for this. You can also use DFS, but you can think on that later. Yeah, thank you.